I'm just going to start with something that we covered in the last session, and it actually raised a lot of questions, and I got a lot of emails about this. So this was the idea of having a ledger with hash pointers. This whole idea that I had a bunch of transactions. So for example, I have transaction 1, and then I had my transaction 2, which included a pointer to transaction 1, right? And so on. So I had another transaction after this that had a pointer to transaction 2. And we said that these are actually hash pointers. So when I say that transaction 2 has a pointer to transaction 1, what I actually mean is that the hash of transaction 1 is saved in transaction 2. So something that was a little bit vague for a lot of people was, why do I have to change transaction 2 if I change transaction 1? So here's the thing. Let's say that I create transaction 1, and let's say it has a bunch of fields in there. So it has, for example, a recipient. It has like an amount. I don't know. It maybe has a timestamp and all these things. So I take all of this transaction as a single string, of zeros and ones, and I just compute its hash. So I would say H1 is the hash of transaction 1. And then when I want to create transaction 2 is going to have a field in it. And this field is going to be the hash of the previous transaction. And the value that I'm going to put there is H1. And then transaction 2 has all the values that the previous one had as well. So all the same fields. And now I'm going to hash all of this, including the hash of transaction 1, which was already included in transaction 2. And then I'm going to say that H2 is the hash of all of this. So you see, the point here is that if I ever want to change transaction 1 later in the future, then changing transaction 1 would change the hash of transaction 1, which was H1. But this hash was written somewhere in transaction 2, so I have to change that pointer there in transaction 2, but that changes the string that encoded transaction 2. So this changes the hash of transaction 2. And then the same thing happens all the way. So this was the idea we had in the last session, that if I change anything in the past, I have to change every transaction that comes after it. So as someone who's just keeping track of this ledger and wants to make sure that I'm not changing anything, you can just keep track of the hash of the last transaction. That's the only thing you need to know. Okay, so this was just a clarification from the last session. Today we're going to actually talk about Merkle trees. So remember the setting that I talked about at the end of the previous session, and the setting was that you're a bank and you have 2 different branches. So let's say that you have a branch here in Hong Kong, and then you have another branch, let's say in Shanghai. And the idea was that people just make some deposits. So let's just give a name to the person who makes a deposit. So let's say Alice makes a deposit. Let's say she deposits $100 in Hong Kong. And she's supposed to receive this $100 later on in Shanghai. And let's say that someone else, so let's say Bob, is putting maybe another $100, and I don't know, Carol is putting $150. So you have a list of people, and these people all came to the Hong Kong branch and made deposits today. And then they want to go to the other branch and later on take their money back. Now, we said that these 2 branches can communicate, but the communication has to be really short. So I have some sort of a communication mechanism here. And let's say that it's one way. Let's say that only the deposit taking branch can send a message to the other branch, because we don't need any other thing here. But this communication channel, whatever it is, we are assuming two things about it. We are assuming that it's unsafe, and we are also assuming that it's very expensive. Okay, so what does unsafe mean? It means that anything that I send on this channel can potentially be seen by a hacker or by anyone, because we just assume if a hacker can see it, maybe they'll publish it and then everyone would know it. So any message that you send from this side to this side will be seen by anyone. And it's also expensive, so we want to send a really short message as far as possible. But what are the properties that I would like to have? So let's just write down the properties again. This is something we do very often in this course. We just set down what it is that we want to achieve. So, of course, I want to make sure that anyone who made a deposit can take their deposit back. And I want to make sure that anyone can take their deposit back exactly once. So every deposit can be taken back, let's say. But the second part is that it can be taken back exactly once. So no one can reclaim the same deposit twice. I write reclaim twice, but I mean the same deposit. I'm just too lazy to write it. Okay, so that's the first thing that we want. Of course, I want to make sure that the message that goes from one branch, Hong Kong, to the other branch is really short. That's the other thing. Let's say I give this message a name. So let's say I call this message M. I want M to be short. But I also need some privacy properties, right? So I'm sending this message M, and I'm saying that this channel is unsafe. So anyone else can potentially see my message. So by just seeing the message M, no one should be able to find out anything about the deposits and the depositors. So none of the IDs of the depositors or the amounts of the deposits should be known by just sending this message M. So another way of saying that is M does not leak any data. Okay. But additionally, we said that whenever someone makes a deposit, we give them a proof of deposit. So when Alice makes a deposit of, let's say, $100, the Hong Kong branch will give her some proof. Let's call it P1. When Bob makes a deposit, the Hong Kong branch will give him a proof P2, P3, and so on. And these proofs, they don't have to be generated immediately. So you can just wait for all the deposits to happen. You can imagine that everyone deposits in the morning, and then you give everyone the proofs in the afternoon. But then the idea is that later on, like in the evening, you send this one message M from this branch to the other branch. And then maybe the next day or the next week, these people should be able to go to the other branch and give this proof to this other branch. So let's say Alice gives P1 to the Shanghai branch, and then this branch should be able to verify that Alice actually deposited $100 in Hong Kong. Okay. Now, if you think of this traditionally in the way that banks worked before the internet or before telecommunications, generally, we didn't have this message M here, right? So if you were, for example, banking, I don't know, in the 1800s, you would just deposit, you would get a piece of paper that was your proof of deposit, and maybe this piece of paper had some security measures built into it, I don't know, some specific type of signature or something, so that when you went to the other branch, that branch was able to somehow make sure that this came from the other branch of the same bank, right? But of course, the problem here is the problem of forgery. So if, let's say, Alice deposits $100 here, and then the Hong Kong branch gives her some proof P1, maybe Bob can just take the same P1 without actually depositing $100 here and somehow copy it and then go to the other branch and try to scam them and get $100 back. Right, so this is like as old as time. People have had these problems forever. But the way we're going to solve it is using this extra message M that the first branch is sending to the second branch. So somehow the idea is that I'm going to use this message M to verify that these proofs that people are submitting are actually not fake, that they're real proofs. Okay. So again, every depositor, let's say depositor number I receives a proof, and I call this proof PI. And again, for our use cases, we are just working with strings, so sequences of zeros and ones. So this M is a string, these proofs are strings. So whenever I don't say the type of something, it's always a string. So every depositor receives a proof. And then the idea is that the second branch should be able to verify every proof. So it is possible to verify every PI using M. These are the properties that we want. Now, it's very common in cryptography that when you first see the properties, you might think that this is impossible. But actually, we will see that it is not impossible, and we will find a way to do this. Okay, so first of all, I want to send a single message M from my first branch to my second branch. What can this single message be? It should somehow summarize all the transactions here. It should summarize all the deposits. Now, we've already seen in the case of the ledger here that if I wanted to keep track of the entire history, I could simply keep track of the hash of the last transaction, right? And I was seeing that, okay, if I have the hash of transaction 3 and then the bank tries to add transaction 4 here, I could just check that it has the correct hash of transaction 3, and that would mean that everything else was correct as well. Now, I want to use a similar idea here. So I want to make sure that this message M is somehow a hash that contains all of these proofs, P1, P2, P3, so on. Okay, or somehow, well, if not all the proofs, at least all the identities and all the amounts here. Now, how can I do that? Oh, I need one other property as well, but let me just give you the simple solution, and then we will talk about why this is not good, and we will add another property, and then we'll make our solution better. So the first solution that comes to mind is, let's just use a ledger like this one. So here I have Alice, and she's putting $100 in. So I can create my first transaction, and I can just put this information in my first transaction. I can say, well, let's put a number here showing that this is transaction 1. Then I can put Alice's identity. I can say Alice was the person who made this deposit. Of course, in the real world, we will need more identification here. And then I'll just write down the amount of the deposit. It was like $100. So this is my first transaction. Right? Then I can create a second transaction. This is transaction 2. It will have a pointer to the first transaction, and then it will contain the information about the new deposit. So I would just say that this is Bob, and he's depositing $100 as well. This is transaction 2. And then similarly, I will just create transaction 3, which has the sequence number, a pointer to the previous transaction, the name of the person, and the amount. Okay. Now I can create all of these transactions and just create a ledger like this. And then at the end of the day, when I have the very last transaction, I can just take the hash of the last transaction and I can say my message M is this hash. So I can just take the hash of the last transaction and send it from this branch to this branch. But would this actually work? Well, the hash that I'm sending is actually, as we've seen before, a commitment to all the transactions. So when I send this hash, I'm basically making sure that none of these transactions can change in a sense, right? But now I have to figure out how to give a proof to each one of my depositors here. Well, the way I can give a proof to a depositor is that, well, let's say I have just these 3 deposits just to make life easier. What does the second branch know? The second branch knows the hash of this last transaction, transaction 3. So in case of Carol, I can just tell her, you can go to the other branch and you can just bring this transaction with you. So I can say that P3 is just transaction 3. Right? And remember that this M was the hash of transaction 3. So in this case, Carol can just go to the other branch. She can say, here's a transaction. Here's a deposit that I made in Hong Kong. And then the other branch just hashes it and checks if the hash of this transaction matches the hash that they received from Hong Kong. And if it matches, then the other branch knows, the Shanghai branch knows that Carol really made $150 deposit in Hong Kong and then pays $150 back to her. But now let's see what happens in case of Bob. So what happens if Bob wants to prove that he has made a deposit? Now here we run into a problem. The problem is that the other branch has the hash of the last transaction. So it has the hash of Carol's transaction, whereas Bob's transaction was transaction number 2. And it might be that Carol has not gone to the other branch to take her money back yet. So maybe Carol wants to go later, but Bob wants to go sooner and take his money back. So in order to prove that his deposit is somewhere in this ledger, Bob actually has to provide not only his own transaction, but also Carol's transaction, right? So the proof that Bob has to provide is actually Carol's transaction and also his own transaction. Now, the way it works is that Bob brings these 2 transactions to the other branch. So the branch first hashes this transaction and sees that it matches the message that they received from Hong Kong. So they know that transaction 3 is real, but they see that transaction 3 belongs to someone else. So they will not pay that money to Bob. But then this transaction 3 that Bob is giving them already contains the hash of the previous transaction. So now this bank knows the hash of transaction 2. But since they know the hash of transaction 2, and since Bob is providing transaction 2, they can just hash this and they can check if it has the right hash. And if it has the right hash, then they know that transaction 2 was also in the list of transactions. And they check and they see that, okay, this is a transaction that is showing Bob deposited $100. So they will pay Bob his $100 back, right? And in the same way, if Alice wants to get her money, she has to actually provide all of these transactions. So she has to provide transaction 3, transaction 2, and transaction 1. So it's some sort of an unrolling of the hashes. Basically, The only thing that this branch knows is the hash of the last transaction. But if you want to prove that your transaction is somewhere in the ledger, then you can provide all the transactions from your transaction all the way until the end. And then all of these hashes and hash pointers can be checked, and it can be proven that your transaction was actually in the ledger. Okay. So this is the very simple solution that we can come up with. Any questions until here? If you have any questions, please just ask in the chat. Now, this is, of course, not very ideal. Why is it not ideal? Well, I'm pretty happy with this part where I'm sending just a single hash, because this is a very short message. A hash is a very short message. So I have this property. I'm happy with this one. And also the hash that I sent does not really leak any data, right? So if someone from outside this system only sees M, what they're seeing is the hash of the very last transaction. But we had the one-way property of the hashes, so they can't even know the last transaction, let alone the other transactions, because they just have a hash. They just have a hash of the last transaction. So I have this property as well, which is great. Now, every deposit can be taken back, yes, because everyone can provide a verifiable proof of their deposit, so the other branch can verify that and give the money back. How do we make sure that no one can reclaim twice? Well, the other branch can just keep track of all the transactions that are already reclaimed. And remember, our transactions or our deposits actually had a sequence number in them. So if the deposit with sequence number 2 is already reclaimed, then the branch would not allow someone else to, again, claim transaction number 2. So we are fine with this. Now, yeah, every depositor received a proof. We have that. It is possible to prove and to verify every proof using just the single message M that was sent from Hong Kong. Yes, because again, the idea was that Hong Kong only had to send the hash of the very last transaction. And then this was what Shanghai could really rely on. And using this and the proofs, they could just unroll the entire ledger up until the point where it had the transaction that they actually cared about, and they could give things back. So it seems like we have all the properties. But of course, there are two problems here. The first problem is that our proofs are getting too long. So imagine if you want to, let's say, deposit $100 and then get it back on the other side. And maybe there were, I don't know, 10,000 transactions on that day. And then they just print out some big amount of data that shows 10,000 transactions so that you can prove your one transaction. That's one problem. So let's say that I want to also have these additional properties. Let's say I want to have short proofs. Okay. Actually, right now, the problem is that if I have n transactions, the lengths of my proof can become basically omega n, which is too long. Okay. And the other thing is actually, this is not giving much privacy here, if you think about it, because in order to prove her own deposit, Alice has to show 3 transactions. But if she shows these 3 transactions, this means that she, of course, had access to these 3 transactions. They were part of the proof that was given to her by the Hong Kong branch. But that's not great, because this is Carol's transaction and this is Bob's transaction. So Alice can also see who deposited how much money. So basically, everyone can see all the deposits that are happening after their own deposits, which kind of defeats the point. Like, we were trying so hard to make sure that M does not leak any data, But now P1, the proof that we're giving to Alice, is leaking all the personal data of Bob and Carol. Yes. So, no, sorry, no. In the chat, you're asking, does Alice also have P2 and P3? No. Alice only has P1. So by definition, P1 is whatever we give to Alice. But P1 contains transactions 1, 2, and 3. And the reason for that is, suppose that Bob and Carol don't show up to take their money. Alice should still be able to take her money, right? So Alice should be able to go to this branch and prove that transaction 1 was somewhere in the ledger. But in order to prove that transaction 1 was in the ledger, she has to actually also prove the existence of transaction 2 and transaction 3. And the only way that she can do that is by having these transactions, right? So this branch only knows the hash of the last transaction. So this is a problem. So even if P1 contains P2 and P3, Alice cannot distinguish all of them. Yes, she can. That's, again, that's our problem, right? So here P1 actually includes all the data in P2 and P3. So in order to be able to prove her transaction and get her money back, Alice needs to know all the information about the next transactions in this system. And since we wanted to make sure that every deposit can be taken back, we gave that information to Alice, but that means that Alice now knows about transaction 2 and transaction 3. So she knows that Bob deposited $100 and Carol deposited $150. Yeah, so that's a huge problem for us. Okay, so how can we fix this? So we have two problems. Again, we want to have short proofs, and we also want to have privacy for the depositors, which means that I want to make sure that no depositor can see the personal information of any other depositor. Okay. It actually turns out that the second property is a little bit easier to achieve. So how can I make sure that Alice cannot see the data here? Okay, so in the chat, someone is asking, what if someone changes M? Then the depositors can change their proofs. Yeah, so we are assuming that no one can change M. So our setting here is that our branch is sending one message M here. Anyone can see it, but no one can change it. And you can imagine that this message is sent using a digital signature. We will soon see the concept of digital signatures. So let's say this message cannot be forged. This M is definitely coming from the Hong Kong branch, and the Shanghai branch can really rely on that this M is the correct M. But it's just that it's unsafe. So unsafe in the sense that anyone else can see it. So maybe instead of unsafe, it would have been better. Oh, this eraser is weird. And let me see. Okay, maybe I erase it like this. Yes. So instead of unsafe, maybe I should say it's not private, in the sense that someone else can see the message that you're sending here. Yeah, but I'm assuming no one can change it. Okay. So how can I create this privacy for the depositors? Well, what I can do here is that I can just change what the transactions contain, right? So right now, the transactions basically contain pointers to the previous transaction, but they also contain all the personal information. So the name of the depositor and the amount of the deposit. But instead of doing that, I can say I'll just include the hash of these personal data. Okay, so I can say that transaction 1 contains the sequence number 1, but it doesn't contain the words Alice and $100. It just contains the hash of the words Alice and $100. Okay, and Other than this, of course, we will have to add nonces as well. So we can say something like this. Let me erase all of this. Whenever I want to hide something, I can just hash it. That's the lesson here. So I can say that Alice, when she deposits $100, she also gives me a huge random number. Let's call that N1. That's the nonce of Alice. Bob also does the same thing. When he deposits $100, he gives the branch in Hong Kong a random number, N2. Carol gives a random number, N3. Okay. Now, this is how I'm going to create my transactions. I'm going to say that I have this first transaction, which is the transaction made by Alice. It contains a sequence number. Let's say I put the sequence number here, 1. And it should also contain a pointer to the previous transaction, but this is the first transaction, so this pointer is the null pointer. Let's say it's all zeros. This is the pointer to the previous transaction. Or actually, sorry, let me put it in the other order so that it looks better. So this is the transaction number, which is 1, and it also has a pointer to the previous transaction, but this pointer is just all zeros because there is no previous transaction. And then in the transaction itself, I used to include the words Alice and $100. But now instead, I just put the hash of the name, so Alice, concatenated with the amount, so $100, and concatenated with this nonce, this random number that Alice chose, N1. Okay. So that's what I put in this transaction, and this is my first transaction. Now, why am I doing this? Because someone who sees transaction 1 can still see that this is transaction number 1 because the sequence number is there, can see the pointer to the previous transaction, which in this case does not exist, but they cannot see any personal data. They can just see the hash of all those personal data. Okay, so I'm using the hash to hide the personal data that I don't want others to really be able to access. Now, when I create my second transaction, let's say this is transaction 2. Again, it has a sequence number, which is 2, and I just write it there. It has a pointer to the previous transaction. So this is a pointer to the previous transaction. And the way we create pointers is again by hashes. So basically, I just write the hash of transaction 1 here. Okay, that's how transaction 2 points to transaction. And then again, I want to make sure that this transaction says that Bob paid $100, but I don't want that to be easy to access, so I just hash it. I say I take this string that has the name of Bob, concatenated with the amount, which is $100, and concatenated with Bob's random number, N2. Okay. And then I do the same thing for Carol. I'm running out of space here, so sorry about this. This is transaction 3. It has a sequence number. It has a pointer to the previous transaction. And it just has the hash of the string that says Carol deposited $150 and her nonce was N3. Okay. Now, if I create a ledger like this, then everything works out, right? Because let's again look at this from the point of view of the different people here. So Carol has the last transaction. So that's the proof that Hong Kong has given to Carol. So she can just take this last transaction to the other branch, and the other branch just computes the hash of this last transaction, TX3, and sees that this matches the message that was sent from Hong Kong. So this branch in Shanghai now knows that transaction 3 was actually really in the ledger. But now transaction 3 doesn't really contain any information anymore because it just has the hash of Carol's name and how much she deposited and her nonce entry. But Carol knows all of these things. So Carol can just give her name, the amount that she deposited, and this entry to the Shanghai branch. And then again, the Shanghai branch can hash that, and they can see that the hash matches this hash that was written in transaction 3. So they can make sure that transaction 3 really says that Carol put $150, right? And then they can pay it back to Carol. Now let's see what happens for Alice, for example. Alice knows all of these transactions, right? But that's fine because these transactions do not really include any personal information of Bob and Carol anymore because all the personal information are now hashed. So Alice just goes with this proof that she has, which is the sequence of all these transactions. She goes to the Shanghai branch. She shows transaction 3. The Shanghai branch hashes transaction 3, sees that this matches M, which was the message sent from Hong Kong to Shanghai. So this proves that transaction 3 was actually really in the ledger. But then this transaction 3 contains a pointer to the previous transaction. And since transaction 3 is verified, you know that this pointer was real. So now you have the hash of transaction 2. Now you just continue this. Alice is providing transaction 2. So you can verify that the transaction 2 that she's providing is real because it matches this hash. And then this one now contains a hash pointer to transaction 1. And then Alice provides transaction 1. So you can verify that transaction 1 is correct. But now at this point, when you verify that transaction 1 is correct, Alice says, okay, my name is Alice. I have deposited $100 and the nonce is N1. So gives you all these 3 parts. And then as the Shanghai branch, you just hash this string and you see that it matches the hash in transaction 1. You know that Alice deposited $100. You give her the $100 back. Okay? So that's the way this whole system would work. Now, here we actually finally have the privacy for the depositors, right? Because again, if you look at it from the point of view of the different depositors here and the proofs that they're getting, no one gets any information about the deposits that happened before them. So for example, Carol is only getting transaction 3. She will not get any information, not even the hash of transaction 1 or 2. Okay, so, okay, actually transaction 3 contains the hash of transaction 2, that's fine. But my point is like, she doesn't get transaction 1 and 2. She doesn't even get the hash of transaction. Similarly, Bob doesn't really get any information about Alice's transaction. But the other way around doesn't really work. So Alice is still getting all these transactions. But nevertheless, that's fine, because even though Alice gets all the transactions, now Alice has access to all of these transactions only contain the hash of the personal information. And our hashes also have nonces in them because this is the same problem that we saw in the auction example in the last session. We want to make sure that Alice cannot just invert this hash by some sort of trial and error, trying every possible value here. So we have these nonces as well. And so it cannot be brute forced. But anyway, what is Alice really seeing? Alice is just seeing a bunch of mumbo jumbo, some information that makes no sense to her because these are just hashes. So all she knows is that she has to bring this information to the Shanghai branch to get her money back. She doesn't know what this actually means. There is no way for her to invert this hash and find out that this was a deposit by Bob and it was $100, or that this was a deposit by Carol and it was $150. So now, assuming that our hash function is one way, which we always assume because it's a cryptographic hash function, we have finally privacy for depositors. And the idea here, and this is again an idea that we will see over and over again, is to hide data by hashing it. Right? And actually, this is now a new use case of hashing, if you think about it. We've already seen two other major use cases of hashing. One major use case was to commit to some data. And as you're seeing here, for example, by sending this message M, which is the hash of the last transaction, the Hong Kong branch is actually committing to the whole sequence of transactions, right? So commitment was one use case of hashes. The other use case that we saw was using hash pointers. And now we are seeing this completely different use case, which is just for hiding the data. So I'm now hiding the data because I didn't want to put this data, I'm just putting its hash. Okay. But how about the problem of having short proofs? Well, our proofs are definitely shorter now, but just by a constant factor. Because if you think about it, before my transaction used to include all the personal data of Alice and how much she deposited and things like that. And that could potentially be long, right? Especially if you need more identification fields in there. Maybe if you want, I don't know, Alice's ID number or passport number or something like that, then you might have many fields in there in your transaction. But now in this new scheme, we're just hashing all of that, and a hash always has a fixed length. So it doesn't matter how big my original transaction was. Now using this hashing, my new transaction just contains a sequence number and two hashes. One hash is the data, the hash of the personal data in this transaction, and the other hash is just a pointer to the previous transaction. So in that sense, we can say that our proofs are shorter, but I still have this problem that if I have 1 million deposits, or if I have even, let's say, 10,000 deposits, then the first person, Alice here, has to receive all of these transactions. So she's going to have a huge proof. We don't want that. We want to make our proofs even smaller than this. And finally, this is where we get to the point that I want to teach today, which is Merkle trees and how we can make these proofs smaller. Okay, so let me erase this. And the reason I erase it is because I don't want it to remain in the lecture notes. I just want you to know about Merkle trees when you see this lecture notes. Okay, so what's a Merkle tree? The idea is actually very simple. So if you look at this ledger here, what data structure does it remind you of? Okay. We have a question. How can we know the hash of transaction 2 by hashing transaction 3 and checking whether it matches with the message? So the way you can know it is that transaction 3 is part of the proof that they're giving to you. So, and transaction 3 contains the hash of transaction 2. So if someone wants to prove transaction 3, they have to give you transaction 3 so that you can hash it and you see that it matches this message. But when they give you transaction 3, and if it's the correct transaction 3 that has the right hash, then it also includes the hash of the previous transaction. And then you can just continue the same. Okay. So if you look here at this ledger, it's pretty much like a linked list, right? So you've all passed basic data structures. This is a linked list. The only difference is that my pointers are not normal pointers, they're hash pointers. And basically, the problem that I'm trying to solve here is a search problem, right? So if you just think of it as a data structure, the Hong Kong branch is giving you a pointer to the very last item in your linked list. And then whenever someone wants to prove to you that some item is in the linked list, they have to actually guide you through the linked list all the way to the item that they want to prove, right? So if someone wants to prove that transaction 1 is there, they have to give you all the information after transaction 1. Because as the Shanghai branch, you only know the endpoint of this linked list, and you just have to traverse it all the way until you reach what you were searching. And basically, these proofs that we had here, these were guides for how to traverse this data structure, how to walk through this linked list that uses hash pointers. And of course, the problem with linked lists is that if you want to go from one end to the other end, you have to take n steps. And so since every step had to be guided by this proof that was given to you, then the proofs had to be long. The proofs had to have maybe even lengthen. So now what do we want to do? We want to make the proofs shorter. What kind of data structure are you familiar with that makes it faster to do these kinds of search? I want to just go over my data structure much faster. Well, I can just have a binary tree, right? So I can have a tree. Let's say I have a binary tree like this. Right? And a binary tree that has n elements in it has logarithmic height. So its height is going to be O log n. So if I have n elements, my height is going to be O log n. Okay. And well, one way to implement binary trees is that we can say every item just has a pointer to its parent. Right? That's one way. But another way to implement it is to say that every parent has two pointers, one to its left child and one to its right child. Right? So these are the two general ways that we usually look at a tree data structure. Now, in our case, again, I want to use hash pointers. And as we saw before, what I did was that I just gave a pointer to some part of the data structure. And the idea was that I should be able to start from that part and be able to just walk over my data structure. So here, actually, it makes more sense if I have these kinds of pointers. If every node has a pointer to its two children. And then the way that I traverse these things is that I just give a pointer to the root. Okay, so this is just the intuition behind what we're going to do. And the idea is that if the Shanghai branch somehow has a pointer to this root node, then they can, and if you want to prove to them that, let's say, this node is in the tree, the way you can prove it to them is that you tell the Shanghai branch, the Hong Kong branch already gave you this pointer. So I give you this information. You now know that this node is in the tree. And because you know this node, you know this pointer. So I give you this information so that now you know that this node is in the tree. And since you know this node is proven to you, this pointer is also proven to you. And based on that, I can now give you this. And maybe my transaction is here. Okay, so that's what we want to do. And intuitively, if I can do this, which I will show you how to do very soon, then the length of the proof would always be logarithmic, because I always have to just say in my proof how to traverse the tree from the root to the node that contains my transaction. Whereas previously, I had to start in a linked list. I had to start from the end of the linked list and traverse it all the way back until I get to my transaction. Okay, but what actually is a Merkle tree? So, Merkle tree. Let's say that I have a bunch of transactions or a bunch of deposits. Again, let's do as before. Let's say I have deposit number 1, and this is Alice, and she was depositing $100. So I call this D1, and this is the information in D1. Let's say I have a bunch of other deposits as well. I'm not going to write them out like that. So let's say I have D2, D3, and D4. So let's say I just have 4 deposits. this idea generally works for any number of deposits. I don't have to have 4, but 4 is just as good as any number to give an example. Okay, so here's how I'm going to create my tree. First, I'm going to create some leaves, and I'm going to create one leaf for every deposit. And in these leaves, I'm just going to put the hash of these deposits. So I'm going to create a node in my tree that just has the hash of D1, hash of all this information. Then I'm going to create another node that has the hash of D2. Another node that has the hash of D3. And finally, another node that has the hash of D4. Okay. Let's give these nodes some name. So I don't know, let's call this one E1, or okay, I can call it L1 since it's a leaf in my tree, L2, L3, and this is L4. Okay. Now I'm going to basically create a binary tree here. So I'm going to create one node here that is the parent of both L1 and L2. And I'm going to create another node here, which is the parent of both L3 and L4. Now, what can I call these nodes? I don't know, maybe I call this one B1 and I call this one B2. But what do I want to actually put here? So I can just take the hash of these two nodes and put them in the parent. So I just take the hash of L1 and L2. And whenever I write this, I just mean concatenation. So I'm thinking of L1 and L2 as some sort of a binary representation as a string. And I'm just saying, put these two strings together, take their hash, put that in B1. Okay. And here I would again put the hash of the two children, hash of L3 and L4. Oops. Okay. And finally, I will have a root. Okay. And this root has these two children. And here I just save the hash of B1 and B2. Okay. And let's say this is my root. Or actually, let me just call my root M, because that's the message that I'm going to send from Hong Kong to Shanghai. Okay. So this is the tree that I'm making. It's just a sequence of hashes. So at the bottom level, I just put the hash of all of my actual deposits, hash of deposit 1, hash of deposit 2, and so on. Now, here, I'm taking these two elements. So this was the first hash, this was the second hash. So let's say, I don't know, let's say the hash of D1 was something, just to make it simple. Let's say the hash of D1 was 1, 2, 3, and the hash of D2 was 5, 6, 7. Okay. So what I'm doing here is that I'm computing the hash of 1, 2, 3, 5, 6, 7. So I'm putting these two hashes together, and then again, I'm hashing them. Right? And at every level, I do the same thing. I take the two hashes that I have in my two children, and I just put these two hashes together. I again hash it. Okay? So effectively, this means that this one has the hash of D3, this one has the hash of D4. I'm putting these two together and hashing them. So what I'm actually saving here as B2 is the hash of D3 concatenated with the hash of D4. Okay. So this is how this thing works. Every node of my tree is just a hash, but it's created by taking the two children, putting them together and hashing. Okay. Now, this tree is actually also a commitment to all of these deposits, if you think about it. Because if I change any of my deposits, let's say I'm the Hong Kong branch, and I've created this tree, and I've sent the value M. This is called the Merkle root. So the value, the hash that is at the root of the tree. And yeah, of course, this is also called the Merkle tree. I forgot to say that. So if I send this hash to the other branch, then I can no longer change any of the deposits. I've basically committed to all the deposits. Because, for example, if I change D3, then this changes the hash of D3, which means it changes L3. But if L3 changes, then the thing that is hashed here changes, so the hash changes, so B2 changes. But if B2 changes, then this hash has to change, so M changes. So no matter what you change here, your Merkle root will always change. So if you just give the Merkle root as this M, so instead of just being the hash of a transaction, now this M is the root of my Merkle tree. If I just send this from Hong Kong to Shanghai, then I'm basically committing to all the transactions that happened here. So I cannot change it anymore. But that was not really important for us in this particular use case. What's important for us is that we want to make sure we can give proofs to people. Now, what kind of proof should I give to Alice? So let's say that as the Hong Kong branch, I've already sent this value M to the Shanghai branch, but the Shanghai branch only knows M. What should I give to Alice so that she's able to prove that she made this deposit D1? Just write in the chat, which one of the strings in this picture should I give to Alice? So you see the Shanghai branch only knows M. They only know the hash of this root of the Merkle tree. Okay, we have some good answers. So B1 concatenated with B2, B2 and L2. Nice. It's actually almost all of the things that you're saying. Yes. So basically, I have to give her L1, L2, B1, and B2. I mean, L1 is something that she can compute on her own, but let's give it to her anyway. So here's the thing. What do we want to make sure can happen? We want to make sure that the Shanghai branch can start at the top here and can just traverse the tree until they get to this point, to L1, which has the hash of D1. And then since Alice is providing D1 itself, Alice is saying, here's my deposit, they can just check the hash. But in order to do that, I have to actually be able to traverse this tree. So let's say I'm the Shanghai branch. I'm starting at the top here. Alice wants to prove to me that the left child is B1. But how can she prove to me that the left child is B1? She can provide both B1 and B2. If she provides both B1 and B2, then as the Shanghai branch, I can put B1 and B2 together, hash it. I can see that it has the correct hash that I received from the Hong Kong branch. And so I can be sure that the children of the root are B1 and B2. And this proves to me that B1 was a node that was actually in the tree. So Alice should give me B2, and she should also give me B1. But at this point, when she gives me these two things, I can basically traverse this edge, and I can be sure that B1 is in my tree. But now, that's not what Alice wanted to prove. Alice wanted to actually prove that L1 is in the tree. So, but now as the Shanghai branch, I'm convinced that B1 was in the tree. So if Alice just gives me L1 and L2, then I can, again, put these two together, and I can see that, okay, if I put L1 and L2 together and hash them, I will get B1. I can verify that, and I already knew that B1 is in the tree, so this proves to me that L1 and L2 are in the tree. Okay, now that I know that L1 and L2 are in the tree, Alice says L1 is my transaction, my deposit, and here's the actual deposit. So she gives me D1. But when she gives me D1, I can just hash D1 and I can see that the hash of D1 is L1. So I can verify that D1 was also in the tree. Okay? So the information that she had to give me was actually these parts of the tree. So she had to give me, well, I already had M. This was something that was given to me by the Hong Kong branch. Alice had to give me B1 and B2 and L1 and L2, and of course, the deposits. So this is the proof that Alice gives me. Alice gives me B1, B2, L1, L2, and the deposit. Okay. Now, similarly, if I want to prove the existence of D3, let's say, oh, someone is asking also the nonce. Yes, so I'm just assuming that the nonce is also included in the deposit. So let's say yes. You should never forget the nonces. I'm sorry about that. Let's say that the nonce of Alice is also inside this deposit. So when she gives you the deposit information, it contains the nonce. Okay, now if someone wants to prove L3, it's a very similar situation. You just take the path from the root to L3, and you have to prove the existence of everything in that path. And the way that you prove something's existence is by providing that thing and also providing its sibling. So if you want to prove that L3 is there, so you have to first prove that B2 is there. But the way you prove B2 is there is that you provide B2 and you provide B2's sibling, B1, so that the Shanghai branch can take B1 and B2, hash them, and see that the hash matches. But now that you have proven B2 is there, you want to now prove that L3 is there. The way you prove L3 is there is that you provide L3 and you also provide its sibling, L4. And then the bank can just take L3 and L4, hash them, and it sees that it matches B2. It was already proven that B2 is there. So this proves that L3 and L4 are there, which basically proves that D3 is there. Okay. So now here's my question. What is our proof length? So how long can our proofs get? Just tell me in the chat. Yes, it's O log n, and yes, the constant factor is 2. Yes, it's actually 2 times log n, maybe +1, -1. I don't really care about that because you have to maybe count whether you want to put m in there, whether you want to consider the deposit itself as part of the proof, or you think that deposit is something else. Yes, but this is O log n. Or to be much more specific, it's twice log n plus some constant, and this constant is like the overhead that you have for giving the deposit itself. Like, I don't know how many fields you have here. You might have a lot of information in the deposit itself, but whatever it is, it's a constant value. So yes, it's O log n. And why is the constant factor 2? Because, well, the depth of my tree is log n. And whenever I want to prove the existence of a particular transaction, what I have to do is to just go through these transactions, start from the root, go all the way until I reach the leaf that contained that transaction's hash, right? And I have to prove the existence of everything in this path. But whenever I want to prove something's existence, I have no way but to also prove the existence of its sibling. So I have a path of length log n. I have to prove everything in this path, and I have to prove the siblings of everything in this path. So it takes 2 log n. Okay. Nice. So now let's just check that we have all the properties. So first of all, every deposit can be taken back because every deposit can be proven. You can prove the existence of a deposit that was actually in the tree. And I mean, we talked so much about how to prove it, so yes, we can do that. Again, to make sure that no one can reclaim twice, the Shanghai branch can just keep track of all the deposits that are already paid back. So if the Shanghai branch pays, for example, deposit number 3, then they will just keep track of the number of this deposit. Every deposit had a sequence number. Or they can keep track of its hash. It doesn't matter. As long as they keep track of what they've paid and they don't pay it twice, it's fine. Okay? So the message was supposed to be short. Actually, the length of our message did not change at all. Our message used to be just a single hash, and it's still a single hash. So the message I'm sending is just the hash at the root of my Merkle tree. So again, if you want to have the data structure kind of intuition, I'm just sending a pointer to the top, to the root of the tree, right? So that's constant size. And this pointer should not leak anything. Well, of course, it doesn't leak anything because we have so many hashes here. In order to leak something, you should be able to invert these hashes, and our hash functions are one-way. So no, none of this information is leaked. Yeah, every depositor receives a proof, and it is possible to verify every proof. But again, very important, you need that one initial pointer. You need that message from Hong Kong to Shanghai to verify the proofs. So because every proof starts at the top of the tree, and you should know what the top of the tree is. And that's what the Hong Kong branch sent. Okay, so it is possible to verify every proof using M, but it's also impossible to verify it without M. So we have this additional property now as well. If you agree that log n is short enough, it's actually possible to have even shorter proofs than this. But for now, we are happy with this. So I have a proof of logarithmic length. And I also have privacy for my depositors. And this is, again, exactly the same argument as before. You see, in my tree, I'm never actually putting any of the deposits. I'm just putting the hashes of these deposits. So even if someone somehow magically finds out all the information in my tree, so let's say someone, I don't know, has made a lot of deposits, and as part of the proofs that they received all of the tree. So they can somehow recreate the entire tree. They would only see the hashes of all these deposits. And since we are assuming that the hash function is one way, there is no way for them to get any information about the deposits themselves, right? So I have this kind of privacy as well. And again, the proof that I'm giving to every depositor is basically how to traverse a path in this tree and their own deposits. So if you look at, for example, deposit 2, only the depositor who actually made this deposit has this information. Everyone else can have at most the hash. So again, this is very safe. Okay. Nice. So we have all of these things. But there is also another point that is interesting here, and not very much for this particular kind of application that we're talking about. But you can also use Merkle trees to show that a particular piece of data is not in your set. So my data here were just the deposits. I don't have to use the deposits. Maybe I could say I have some piece of data, data 1, data 2, data 3, data 4. And then I want to give a proof that a particular entry is there, right? And this would be the proof. But I can also give a proof that a particular entry is not there. And the way I can do that is that I can say the leaves of my tree are in sorted order, right? So if I want to prove the absence of a particular data, I can say, suppose that I always sort these so that D1 is less than D2, less than D3, less than D4, right? And then if I want to prove that a particular piece of data is not there, so let's say I have some D, which is between D2 and D3, and I want to prove that D is not there. I just prove that D2 and D3 are there. And this also proves the path that I have to take in the tree to reach them. So anyone who sees this path can see that these are two consecutive leaves of the tree. And so if you prove two consecutive leaves of the tree, you have proven that there is no data in between them. And this trick only works if you put the data in a sorted order. But that's not too important for us. We are mostly focused on proving the presence of data, not its absence. I just wanted you to know that we can do that as well. Okay, this is it for this session. I will see you on Thursday. And I'm going to stay here, so if you have any questions, just ask in the chat and I'll answer. Yeah, and you can leave. Okay, for the last bit, how does this work? How do we prove that a particular data is not there? So just think of these different pieces of data that we have as some numbers, because at the end of the day, they're strings. They're written using zeros and ones, so I can also think of them as numbers, so I can also sort them, right? So let's say that, or you can also think of them as strings in the English language, and I can sort them alphabetically. So suppose that in my tree, I have something like this. Okay, let me just draw the tree. And let's say my actual data was a bunch of names or a bunch of numbers. So let's say I had, for example, 2, 5, 17, and 25. So I put them in a sorted order here. So this one will have the hash of 2, this one will have the hash of 5, and of course I will have a nonce and so on. I always use nonces when I use my hash. So, but let's say that I want to prove that 6 is not there. Proof 6 is not in this Merkle tree. Okay. If I want to prove that 6 is not here, I can just prove that 5 and 17, so the number that was immediately before 6 and the number that was immediately after 6 are in the tree. How do I prove that 5 is in the tree? Well, I have to give you the root of the tree. So I have to give you this information. Then I have to prove this node to you. And the way I do that is by giving its sibling. And then I have to prove that 5 is there. And the way I did that was by proving its sibling. Okay, maybe this wasn't, this example doesn't look great when you have a small tree. So it would have been much better if I had a larger tree. But when I'm giving this proof, I'm not only proving that 5 is in the tree, I'm also proving where 5 is in the tree, right? Because if you think about it, at this point, when I wanted to, let's say this was my root, and let's say this was B1 and this was B2. When I want to prove that B1 is in the tree, I'm not only proving that B1 is in the tree, I'm also proving that B1 is the left child of M. Because I give you B1 and B2, you put these two together in this order, hash them, and you see that the hash is M. So I'm proving that B1 is the left child of M. And then I'm proving that 5 is the right child of B1. So basically, I'm proving that if I take this path in the tree, it will reach a node that has the value of 5. Now, similarly, when I want to prove that 17 is in my tree, what I'm actually proving is that if I take this path in the tree, I will reach 17. Now, by just having these two paths and by knowing the depths of the tree, I can say for sure that a path that goes like this is going to go to the second leaf, and a path that goes like this is going to go to the third leaf. So if I know that my second leaf is 5 and my third leaf is 17, and if I also have the rule that all of my leaves are in sorted order, then I know that 6 is not there. Because if 6 were there, it had to be between 5 and 17, but 5 is in the second leaf and 17 is in the third leaf, so there can be nothing in between them. That's the idea. That's how you prove that something is not in a Merkle tree. And this is also going to take a proof of length log n, but of course the constant factor is larger. It's like 4 log n instead of 2 log n, because you have to prove 2 paths in the tree. Okay. Now, another question is, how would we add a new transaction? So that's actually very important. We cannot add a new transaction, because any change in the tree would change the root here. So the way this works is, I was actually very careful about how I was setting this up. I was saying that everyone makes their deposits in the morning and they all get their proofs in the afternoon. So after all the deposits are done, then the Hong Kong branch creates the entire tree at the same time. And after you create the tree, you cannot add or remove anything. But then you can make all these proofs and give them to the people. Okay. Great. I'm going to wait to see if there are any other questions. Yes, it's a hard-coded tree. And the reason for that is that we are also going to use this as kind of a commitment scheme to commit to a lot of data. And whenever we commit to something, we don't want it to be able to change. So it's an immutable tree, to use the right word here. Okay, it seems there are no more questions. I'll see you in 2 days.